guess I should probably start with either an apology or a word of warning, which is that although this is a CITA talk, I'm very much not an astrophysicist. I'm a bit more of a formal theorist. My background is in string theory. And so because of that, there might be a bit of an impedance mismatch between the audience and me. So I would like to try and proceed a bit slowly and really encourage everyone to ask questions, to interrupt if something's not clear or if something's too clear and you want me to move faster, all that stuff. So the subject of my talk is quantum gravity in de Sitter space and some recent ideas and progress that we have been making on the subject. Before, however, I dive into all of that, I thought it might be useful to begin with a bit of a general overview. So, of course, as we all know, classical general relativity and cosmology are very successful subjects, but they're successful theories that fail to answer several important questions, namely those involving the quantum nature of space-time, which is important when curvatures are Border-Planck scale, such as in the very early universe near the Big Bang singularity. But also, classical cosmology does not answer questions involving the interpretation of cosmological horizons. So Hawking and Bekenstein taught us that to each event horizon we should associate an entropy. And in the case of black hole physics, we have now a pretty good idea of what that entropy means and what its origin is. But in the case of cosmological horizons, such as the horizons that appear in an inflating spacetime, we really have no such simple explanation. And to answer these sorts of questions, we really need a theory that goes beyond the classical cosmology, and we need to start thinking about quantum cosmology. Now, quantum cosmology is a notoriously confusing subject. It's one of, I think, the most confusing subjects in theoretical physics, in part because even the basic structure of the theory, I think, at this point is very much up for debate. So we are now talking about a quantum theory of gravity. So we don't even know what the basic degrees of freedom of the theory are. For example, what is the Hilbert space that describes the space of states of the system? What is the Hamiltonian that describes time evolution in the theory? And moreover, I think, the most important question is whether these standard familiar quantum mechanical notions are really even the right language that we should be using to describe quantum cosmology. For example, in quantum mechanics, one of the most cherished notions is that of unitarity, which says that the number of degrees of freedom of a system does not change in time. And it's very difficult to square the notion of a unitary theory with a theory where space-time has a beginning at some definite time. If the number of degrees of freedom does not change in time, then it's difficult to understand how time could have had a beginning. And moreover, this question becomes sharper in universes which are inflating, because if the volume of space-time is expanding exponentially in time, then how can that be consistent with the statement that the number of degrees of freedom does not change in time? So we won't, of course, be able to answer all of these questions. But today, I would like to begin to describe a set of rather explicit computations where we can address these sort of issues in a slightly more quantitative manner. So the strategy that I will use is to remember that over the last several decades, a series of similar problems have arisen in the case of black hole physics. So in black holes, we also have the problem of understanding the structure of space-time at the core of a black hole, where curvatures become Planck scale. And moreover, we have questions involving the nature and the origin of the entropy of a black hole horizon. And in both of those cases, we were able to use string theory, which is a theory of quantum gravity, to answer these rather difficult questions involving the physics of black holes. And the answer in that case was that despite the fact that black holes apparently violate the laws of quantum mechanics because they apparently destroy information, in fact, in a full quantum mechanical description, the theory of black holes is completely consistent with quantum mechanics. And a black hole can be described in a standard quantum mechanical theory with a Hamiltonian and a Hilbert space, just like any other quantum mechanical theory. And so what I would like to now do is take some of the lessons that we have learned from black hole physics and see if we can apply them to this somewhat more confusing subject, which is that of quantum cosmology. Now, there's been, over the last decade or so, a great deal of work on trying to understand cosmology in string theory. In fact, there is an entire body of literature where people construct solutions to the equations of motion of string theory, to the equations of motion of quantum gravity, which describe, I won't say completely realistic cosmological models, but quite realistic cosmological models. Models of cosmology which have all of the features that we expect may be present in any of the cosmological models that we like to apply to the early universe. Now, what I would like to do today, however, something's going on. There we go. What I would like to do today, however, is not try and focus in detail on the construction of quasi-realistic models of cosmology in string theory, but rather what I would like to do today is step back just a little bit and see if we can use some of the techniques that we have learned in the study of quantum black holes to answer some of these very basic conceptual questions about quantum gravity in a cosmological setting. And so my goal is to really try and take the lessons of quantum black hole physics and distill them down to their basic essence and see if we can apply this to the theory of cosmology. Now, one reason why I'm going to take this approach is that if you actually look at the models of cosmology that one can construct in string theory, in fact, they're really quite complicated. And in general, one ends up needing to use the techniques of effective field theory or approximate techniques in order to construct models of cosmology or inflation in string theory. And if the constructions that people use, such as KKLT and collaborators, are Baroque, then the dynamics associated with these constructions are even more so. So when one tries to construct inflating solutions of string theory, not only are the constructions themselves complicated, but what one finds is that the solutions include not just a single inflating vacuum, for example, but rather a very large number of inflating vacua, and there are instabilities. These vacua can transition between one another. And so if the construction is Baroque, then the dynamics are even more so. So I understand that you had a talk last week on something related to this. Lenny Susskind, I guess, is here next week, and my hunch is that he'll also talk about something related to this. So my approach today will be somewhat different. Rather than trying to comprehend the full complicated glory of string cosmology, instead what I would like to do is see if we can understand a very, very simple model of quantum cosmology where we can at least address some basic conceptual issues in a quantitative manner. Now, before I dive into detail, let me also encourage everyone to interrupt me and ask questions or interrupt me for not to ask a question at any point. So before diving into any detail and doing any specific computations, what I would like to do first is tell you in a little bit of detail exactly what it is I am going to try and compute. So I am trying to study cosmology in a quantum mechanical setting. So classically, of course, the universe is given by some curved spacetime, a specific curved spacetime. But if we're working in a quantum mechanical setting, then the state of the universe should not be described by a particular spacetime with a particular geometry, but rather by a wave function, which is supported on a whole family of geometries. So, for example, if you can imagine a universe which has some space-like slice, and then you could consider the metric or the geometry of that space-like slice h, and then the state would be described by some wave function psi of h, which is a function of all possible geometries on that space-like slice. And one can not only vary the geometry of that space-like slice, but also its topology. And so the actual state of the universe will be a superposition of all such possible geometries and topologies. Now, that sounds like a very complicated object indeed. So one might ask, what principle could you use to figure out the wave function of the universe? Now, this wave function must solve the Wheeler-DeWitt equation, which is the gravitational analog of the Schrödinger equation. So Schrödinger's equation written for general relativity. And in fact, there is a very natural proposal for this wave function. It's a proposal that was given more than 30 years ago by Hartle and Hawking. And they proposed that the wave function of the universe be determined by computing a path integral. So as you know, in quantum mechanics, a wave function can be determined by computing a path integral, which will evolve you from some initial state to the final state where you're computing the components of the wave function. And Hartle and Hawking proposed that the state of the universe be given by a similar path integral. And here, the way that the path integral is constructed is you fix your space-like slice, you fix the geometry on the space-like slice, and then you integrate over all possible geometries which have that space-like slice as their boundary. So, for example, if your space-like slice is three-dimensional, you would integrate over an infinite family of four-dimensional geometries. And as usual in quantum mechanics, you would weight that integral with the exponential of minus the action. And then this path integral is the usual sort of path integral that you do in quantum mechanics, which would construct for you a wave function. Now, this might sound at first sight rather abstract, but in fact, as we see when we begin to unpack this Hartle-Hawking wave function in a little bit more detail, for those of you who do computations of fluctuations during inflation, this is precisely the state that one uses when one constructs correlation functions for the inflaton field during inflation, for example. So this is not merely an object of purely formal interest, but anyone who's, for example, calculating fluctutions in the cosmic microwave background by studying the perturbations of the inflaton is using precisely this Hartle-Hawking state computed in an inflationary setting. And one of the deep lessons that we've learned over the past decade from string theory, from holography, from ADS-CFT, is that, in fact, this Hartle-Hawking proposal for the wave function of the universe is right, at least in some settings. In a particular sort of universe, namely the geometry of anti-de Sitter space, the Hartle-Hawking state exists, it can be constructed, and it is, in fact, just the partition function of a standard quantum mechanical system, which is a conformal field theory, which is the CFT of the ADS-CFT correspondence. So one of the things that we've learned over the last...
So can I just... all right. Number one, why is it that it is the Euclideanized path integral? I mean, who is it that said it? I mean, I know that that's a Hawking mantra,
yes.
But the way they always talk about it is they say it's a computational device with, almost always,
yes.
a computational device, and then I can do a Wick rotation or whatever
yes.
into the real world.
That's right. And that's
So
precisely...
but this is much more than that, because by doing the Euclidean path integral,
yes.
I'm essentially operating in a thermodynamic vision. And then
yes.
I am interpolating from that to real time.
Correct. So,
So
yeah, okay,
so
good.
this is a big thing that you're already imposing
Yes.
upon the attempt to move
Absolutely. So, yes. So, okay, let's unpack those ideas a little bit. So, one initial motivation for this Hartle-Hawking proposal is that this construction, so this is an integral, I haven't been terribly specific here yet, but this is an integral over Euclidean geometries. And, of course, we live in a Lorentzian space. But this prescription, where one integrates over Euclidean solutions, Euclidean configurations, is for normal quantum mechanical systems, such as quantum field theories in Minkowski space, standard quantum mechanical systems, precisely what one can use to construct the vacuum state theory. So part of the motivation for this Hartle-Hawking proposal was that it is the natural generalization of the notion of a vacuum state to that of quantum gravity. Now, the problem with this proposal is that at this point, this is just a series of symbols that one doesn't actually know how to compute. So one very rarely knows how to compute a path integral in quantum field theory, much less in quantum gravity, where you're imagining integrating over some infinite dimensional space of geometries. However, one of the remarkable things that we've been able to do in ADS-CFT is see that in the theories of quantum gravity that we do know how to define precisely, this is precisely what you are computing. It is an integral over a space of metrics in Euclidean signature. This is not the way that a holographic or ADS-CFT correspondence is usually phrased, but this is one interpretation of that. So the reason why
what's the extra dimension in this picture?
In the ADS-CFT picture, the extra dimension is the radial dimension, which holographically reconstructs the boundary quantum field theory.
So is it the temperature?
No, it's the time direction. It's a Euclidean version of the time direction. No, it's not periodically identified in any way, no.
So naturally, it only becomes periodically identified when you actually have a data physical.
Yeah. Okay. If you want to use that language, it's not periodically identified. So, okay. When I turn to this computation in de Sitter space, it'll be a little bit more down to earth, and you'll see that what I'm writing down here actually will make rather specific contact with things that those of us who do computations in inflation all know very well. And so at this point, this might sound like a rather abstract statement, but it's something that people who study the growth of cosmological perturbations during inflation use every day, although they might not phrase it in this more formal language. Okay, so I told you that my goal was to find a simple model of gravity where I can perform computations in quantum cosmology explicitly and try and answer some of these difficult conceptual questions that I mentioned at the beginning of this talk. So I will be studying the theory of quantum gravity in de Sitter space. So de Sitter space is the maximally symmetric solution of general relativity with a positive cosmological constant. So this is the action of general relativity. And if you have a positive cosmological constant, lambda, which I've written as 2 over L squared here, where L is a dimensional constant with dimensions of length, then the maximally symmetric solution of this theory is de Sitter space, which is a space-time that inflates eternally. So during inflation, the universe looked approximately de Sitter if, as observations indicate, the cosmological constant is non-zero, then we are right now, as we speak, entering a phase of exponential expansion where the universe will approach de Sitter in the far future. So de Sitter space is, of course, a very important geometry which we would like to understand if we want to understand our universe. And the statement that I would like to make and use for the rest of this talk today is that although for realistic theories of cosmology, such as general relativity in 4 dimensions, coupled to whatever matter we have, standard model, so on and so forth, this theory is difficult to study. In 2 plus 1 dimensions, in 3 space-time dimensions, this theory is exactly solvable in the sense that I can compute the partition function. I can compute integrals over spaces of metrics. And unlike the usual case in quantum field theory or quantum gravity, I can actually define precisely what I mean by an integral over a space of metrics, and I can extract physics from it.
Are you going to let Z depend upon parameters, or
Yes.
is it just going to be a number?
It'll depend upon parameters. It will depend on the coupling constants of the theory.
Okay.
For example, it will depend on the cosmological constant. And at the very end, in the last slide, we will see that under some cases, the cosmological constant will need to be quantized. If one is studying a quantum theory of cosmology, then one expects the coupling constants to be quantized. And so the cosmological constant must be quantized. And indeed, in simple theories of 3-dimensional gravity, one can see explicitly that the cosmological constant is quantized. Indeed, we will see that the cosmological constant will need to satisfy some sort of number theoretic equations.
I just want to expand a bit further.
Yes.
Z is a number ultimately, so
Yes.
what good is it?
Well,
I guess
good.
you tell us.
I will tell you. Okay.
It's everything, as you know.
No,
It's not a
no,
number.
that is the right question.
It is
No,
the-
that is the right question.
No, it's the free energy. It's just that you are assuming certain
Okay.
things are fixed.
Yes. No, good. Why? Okay, there's a reason why I had this slide first. Okay. What is this slide? This is the wave function, which is a path integral as a function of some boundary data. So it's a function of boundary data. So if you want to compute the norm of this state, that is the partition function. So the first thing that one can ask is whether this is finite or not. Okay. That's the statement as to whether or not this Hartle-Hawking state lives in the Hilbert space with finite form.
But this is infinite in quantum field theory, so you know, it's infinite.
That's not in every quantum field theory. In quantum field theories where we know how to define this path integral precisely, it's not. So 3-dimensional general relativity is a quantum theory with no local degrees of freedom. It's closer to a theory of quantum mechanics than a quantum field theory. If you want to think of it as being close to a quantum field theory, you should think of it as being a topological quantum field theory like Chern-Simons theory, where this partition function is not infinite, it's a number. That number contains some interesting dependence on the parameters. So for example, okay, I don't want to get too far afield, but you're absolutely correct that this is a number. But it's a number that contains physics.
I cannot resist, as usual, but to give this a different terminology, because everybody in CITA is essentially a Bayesian. And Z is the evidence. It is the evidence of the theory. The Bayesian evidence of the theory is Z. It's a pretty neat statement. It's actually quite profound. But, the evidence should be finite. It should be a number. See, it's a nice wording because.
Okay.
Margie, you got that?
Okay, why don't I continue? You feel free to attach any interesting words that you want. I'm not going to object. So, what would I like to do? Well, I would like to tell you how it is I'm going to do this path integral. And then I would like to tell you what it is that I'm going to conclude from the outcome of my computation. And along the way, I really want to focus not on the technicalities, but really on the conceptual issues. Okay. So, how would we begin attacking a path integral of the sort that we're doing here? So, the first way that we would start by doing a path integral in quantum mechanics, quantum field theory, however, is we would start by doing a saddle point approximation. So what does that mean? That would mean we would need to find the stationary points of this integral, which are places where the derivative of the action vanishes. In the case of a quantum field theory or any other theory with an infinite number of degrees of freedom, this is the place where the variational derivative of the action vanishes, meaning that the saddle point contributions to this path integral come from solutions to the classical equations of motion, where the variation of the action with respect to the metric is equal to 0. Right? Those are the classical equations of motion. And so, at leading order, the path integral will be given as a sum of the solutions of the equations of motion of the classical action evaluated on that solution. Now, of course, life is more than just classical physics, so we would like to start computing quantum corrections to this path integral. How do we do that? Well, we need to identify a coupling constant in the theory. So the action of the theory is that of general relativity with a positive cosmological constant. Now, in 3 dimensions, Newton's constant has dimensions of length. The cosmological constant has dimensions of 1 over length squared. So I'm using here units where the speed of light at h bar are set equal to 1. So that means there's only one dimensionless coupling constant in the theory, which I'll call k, and that is the cosmological constant in Planck units. It's the curvature radius in units of Newton's constant. And this is the quantity which, if I restored my units of h bar, would go like 1 over h bar.
So, you don't mean L squared?
I mean, so you're used to 4 dimensions where g has units of length squared. I'm working in 3 dimensions, 2 plus 1 dimensions where g has units of length. So there's one dimensionless coupling constant. That coupling constant is 1 over h bar. It's the coupling constant that suppresses quantum mechanical effects. So the classical term, of course, is weighted with a 1 over h bar. So it's weighted with an overall power of the only dimensionless coupling constant in the theory k. And then, if I'm powerful, I can go ahead and start computing quantum corrections. And they will appear as a power series in powers of 1 over h bar. Namely, a power series in powers of the coupling constant 1 over k. And in quantum mechanics, we usually give a name to the successive corrections to the classical action in a perturbation series in 1 over h bar. Those are what we call, so this first term is called the 1-loop correction, the second term is the 2-loop correction, and so on and so forth. And it's in principle straightforward, although in practice usually a difficult task, to go ahead and compute these quantum corrections using the rules of quantum field theory. Now, at this point, I've only been talking about a saddle point approximation to the theory. But the point is that if I can accomplish 2 tasks, then this no longer becomes an approximation, and instead becomes an exact expression for the path integral. Or more precisely, this becomes the definition of the path integral in quantum field theory. So to the extent that we know how to define a path integral in quantum field theory, it is equal to the saddle point approximation if we can find all of the classical solutions to the theory, and if we can identify the infinite series of quantum corrections around each step. Now,
we're going to say that your series will converge.
I will tell you exactly when and when it does not converge.
Okay.
For example, it will only converge when the cosmological constant takes certain quantized values. Now, it's a very special theory. So for those of you who've studied quantum field theory, you very rarely think about quantum field theory path integrals in this language, because you can very rarely do either of these 2 tasks. So I only know of a few very special quantum field theories where one can compute the path integral of this sort. And it's even more remarkable, I think, that there's a theory of quantum gravity where one can compute this partition function. And you can see now why I have focused our attention on a rather simple theory of gravity, namely that of general relativity in two space and one time directions. Because that is a theory where I can actually find all of the classical solutions. In four-dimensional general relativity, this would be a completely hopeless task. There are, even the topological classification of four-dimensional manifolds is incomplete, much less the classification of all possible solutions of general relativity. But in three dimensions, this is in fact an exercise that one can perform with Wikipedia. Okay. And that is in fact how I initially performed the computation. You literally Google spherical tree manifold and go to the Wikipedia page. The next thing that one can do can't be done with Wikipedia, but it's still possible. And that is the computation of the infinite series of perturbative corrections around each solution. That's something that is a bit more technical, and I don't want to go into unless there's particular interest, but that is also something that can be done. Essentially using the methods of topological quantum field theory. But instead, what I would like to focus on is the first bit of this computation where I think about the classical solutions. The reason why I would like to focus on that part of the computation is that there's actually a lot of very interesting physics, even in the set of classical solutions to the equations of motion. And just by studying these classical equations, already one can see how quantum gravitational effects will arise when one studies the quantum cosmology of eternally inflating universes. So in order to understand that, let's step back for a minute. I'll need to tell you a few things about eternal inflation and a few things about de Sitter space. So I apologize to those of you who are already experts in de Sitter space, which might be all of you. But for those of you who might not be, let me just remind you a bit about the geometry and the structure of de Sitter space. So in de Sitter space, the universe inflates eternally. So here I've drawn a picture of the causal structure of de Sitter space. So I've drawn de Sitter space as a square where light rays will travel along 45-degree lines, and time-like observers will travel on lines that are more vertical than 45 degrees. So I've suppressed a few dimensions here. So the spatial slices are going to be spheres, and the sphere has some very large size in the far past. It shrinks down to some finite size at time t equals 0, and then it expands again to infinite size in the far future. And it is this second phase where the universe is expanding at an exponential rate that we usually think of when we think of the inflationary phase at in the early universe. So the important point about the de Sitter universe, however, is that any observer who is sitting at a given point in de Sitter space will eventually lose causal contact with any other observer. So, for example, if I am sitting right here and Amanda is sitting in the back of the room and we are undergoing eternal inflation, then eventually Amanda and I will be receding away from each other at a speed which is faster than the speed of light. So, for example, if I am here and Amanda is over here, as we follow our geodesics through de Sitter space, eventually it will be impossible for one of us to send a light ray to the other. So for this reason, if hell is being stuck in a room with your friends forever, and eternal inflation is the exact opposite, but it's an equally existential nightmare. Now, one of the things that we have learned from the study of black holes over the last 2 decades is that one should really focus only on the physics of a single observer. If one tries to study the quantum mechanics of an observer outside a black hole, simultaneously with the physics of an observer inside the black hole, then you will quickly obtain nonsense. For this reason, we should really focus our attention only on that portion of the geometry which is accessible to a single observer. So this region is called the causal patch, because it's the part of de Sitter space that is within causal contact with an observer. So if I am an observer who is sitting right here at what would be, say, the south pole of the sphere, which is the spatial slice of de Sitter space, then I can be in causal contact only with this diamond-shaped region of de Sitter space, which is the causal patch. And one can write down a metric on the causal patch. Here's the metric that I've written down. So r here is a radial coordinate, so that I, the observer, am sitting at r equals 0. The event horizon, the cosmological horizon behind which I can communicate, is located at r equals pi over 2. You can see that from the metric because that's the place where the coefficient of dt squared shrinks down to 0 size. That's what a horizon is. It's a place where everything becomes infinitely redshifted, meaning that energies are infinitely redshifted, or the coefficient gtt in the metric is going to 0. And there's also an angular direction, which is, at this point, going along for the ride. Remember, I'm in 2 + 1 dimensions, so there are 2 space and 1 time dimension. Now, in order to think about quantum theory in de Sitter space, one must be a little careful. Because unlike in Minkowski space, there is no global notion of conserved energy in de Sitter space. One mathematical way of saying that is that the de Sitter geometry has no time-like vector which generates a symmetry of the geometry. So there's no global notion of energy. However, associated with a given observer, one can always define a notion of energy. What is that notion? Well, it's very simple if you just remember the metric that I wrote down on the previous transparency. So the metric was dr squared minus cosine squared r dt squared plus sine squared r d phi squared. You can see that this metric is independent of t and phi. Components of the metric are independent of t and phi, meaning that it has a time translation symmetry, which will be generated by some operator h, which will become an operator in any quantum theory, which we would call the Hamiltonian. Likewise, there is a rotational symmetry, because the components of the metric are independent of phi, and so the theory will also have an angular momentum operator, which will become an operator that will act on the Hilbert space of states in any quantum theory of de Sitter space. So the states in the theory are described by labeling them with an energy h and an angular momentum j, which describe their transformation properties under these 2 operators, just like in Minkowski space. So now that we have a bit more of an explicit understanding of what physical states look like in de Sitter space, what then is the Hartle-Hawking state that I was going on about at the beginning of this talk? Well, to construct the Hartle-Hawking state, as we saw in the beginning of this talk, we need to go to Euclidean signature. So that's easy enough. We just make the coordinate transformation where we set t equals to it Euclidean. All that does is it gives you a plus sign right here. And then you stare at that metric and you think about it. And the first thing that you notice when you look at that metric is that near r equals pi over 2, sine squared r is approaching 1, so nothing funny is happening here. But cosine squared r is going to 0. So near r equals pi over 2, the metric looks like dr squared plus r squared times dt Euclidean squared. And you'll recognize that as the metric on the flat plane. Dr squared plus r squared times dt Euclidean squared is the metric on the plane, provided this Euclidean time coordinate is periodically identified. The Euclidean time coordinate is the angular direction of one. And in order for a plane not to have a curvature singularity of r equals pi over 2, we need this Euclidean time coordinate to be periodically identified. Now, this phi coordinate is also a periodic variable. R only runs between 0 and pi over 2. So that means that this Euclidean geometry, once we periodically identify this Euclidean time coordinate, is some compact geometry with finite volume. In fact, although it might not be obvious in these coordinates, that geometry is just a three-dimensional sphere. So let's think a little bit about what it meant physically that we periodically identified the Euclidean time coordinate. So time translations are generated by an operator h. And if you wish to identify by translation in time by period 2 pi, then that means we need to generate that identification by the operator e to the minus beta h. E to the minus beta h is the operator that generates a time translation in Euclidean signature. And what is e to the minus beta h? E to the minus beta h is the Boltzmann factor. It's the density matrix of a quantum system at finite temperature. And the temperature, the inverse temperature, theta, is just equal to 2 pi. So here, I've been a little lazy, and I've been using units where I don't have any de Sitter radius anywhere. But really, there's 1 over L squared appearing all over the place. So this is actually 2 pi times L to some power. 2 pi times L. So what this means is that if you want to study physics in de Sitter space, by starting with this Euclidean sphere and then going to Lorentzian signature by doing the coordinate transformation t equals I to Euclidean, then what you're really doing is studying physics at finite temperature. And in fact, any of you who've studied cosmological perturbation theory during inflation have done precisely this. Because you learned that, among other things, during inflation, all of the states in the theory are thermally excited with a temperature that's equal to the inverse curvature scale, or a temperature that's set by the Hubble parameter of de Sitter space. And so the statement that Euclidean continuation of de Sitter space gives you the sphere is nothing more or nothing less than Hawking's famous statement, Gibbons and Hawking's famous statement, that a de Sitter horizon will emit a thermal bath of radiation of the Hawking temperature. And for example, in the study of the growth of fluctuations during inflation, this is precisely the state that one uses when one studies cosmological perturbation theory, where it usually goes into the name of the Bunch-Davies state. But we could just as well call it the Hartle-Hawking state. Now, what is the point? So this is what I was taught when I was a graduate student. But unfortunately, what I was taught when I was a graduate student was wrong. Because I was taught that the geometry I described to you before was the only Euclidean continuation of de Sitter space. But that's just not true. It's the simplest Euclidean continuation of de Sitter space. So for example, previously I mentioned that you had to periodically identify Euclidean time. But one could equally well have obtained a nice solution to the equations of motion, which has every right to be called the Euclidean continuation of de Sitter space, if I'd made a different coordinate, a different identification, where I not just periodically identify Euclidean time, but I also do a rotation in this angle phi. So what is this geometry? Well, this is one of the geometries that I discovered when I went to the Wikipedia page trying to do the path integral of quantum gravity. It's a geometry that's not the three-sphere, but it's got another name. Its name isn't important. It's called the lens space. And it's another solution to the equations of motion. And it's something else that will appear as a saddle point in the path integral of quantum gravity. And the nice thing about the description that I've given here is that we now understand precisely the physical interpretation of the saddle point. Because just like for the three-sphere, the identification was given by the operator e to the beta h, here now, the identification that one does in order to obtain this geometry is given by e to the beta h plus theta j. H here is the Hamiltonian that generates time translations. J is the rotation operator that generates rotations. And beta and theta here are numbers which are determined by this identification. And in particular, if you stare at this for a second, you'll realize that unlike the previous case, where we found the density operator for a canonical ensemble theory at finite temperature, here we have the density operator for a theory at a grand canonical ensemble at finite temperature and finite chemical potential. So let me remind you that when you study physics in the canonical ensemble, you fix the temperature. But if you have, say, a number operator or an angular momentum or any other conserved quantity in the theory, you could also study the theory in grand canonical ensemble, where you introduce a thermodynamic potential, theta, which is the thermodynamic variable conjugate to the angular momentum. So if one wants to use this other geometry to do physics, then what you find is that the horizon of de Sitter space does not emit a bath of radiation at the usual Hawking temperature of de Sitter space. In fact, it emits a bath of Hawking radiation at a temperature which is twice that of de Sitter space, or 3 times that of de Sitter space, or 4 times, depending on the value of that number t. And moreover, unlike the previous result, the radiation that comes out of the de Sitter horizon is not completely isotropic. Because of this additional piece in the wave function, this additional piece in the density operator, this radiation that's now emitted by the cosmological horizon has some preferred angular momentum. So it's not isotropic.
Just a
question.
Quick dumb question. Is there a way of seeing that, are there any restrictions on both P and Q to make sure that that's a manifold, not a multifold? So
Absolutely. So that's the statement that, that's
basically
what I
the
wrote
CP
here.
has to act freely. Okay.
That's the statement that these are 2 integers which share no common factors.
So is it easy to see why that acts freely on the...
It is an exercise for the computer.
It's
It's actually not that hard.
All right.
If you sit down with it, you'll see it.
Okay.
If you sit down with it, you'll see it. But I don't want to go through it for the sake of time. Okay. So what have we identified here? We've identified an infinite number of geometries.
Could you go back to the
Sure.
PQ
Yes.
equals 1. So what exactly is
Okay.
the relationship?
The relationship.
So it's a 1 over P.
Yes. So P and Q are relatively prime. They share
All right,
common
let me
factors.
tell you what I'm
Yeah.
wondering about. So is the Q over P in some sense going to be like an M, an integer?
Q over P is a rational number.
So that's one over, yes.
And in fact, there's one geometry for every rational number.
Okay, so that means good.
So-
Okay, good, yeah, okay, great.
There's a
That
set,
works.
yes,
That works.
okay. Okay, so we've now discovered an infinite number of geometries, all of which are equally deserving of the name the Euclidean continuation of de Sitter. So you might be confused if you hadn't paid attention to the first part of my talk, because you might then be confused and say, which one of these geometries should we use when we study physics in de Sitter space? And the answer is that we use all of them. But we just weight them by a factor, which is their action evaluated using the Einstein-Hilbert action with the positive cosmological constant. Now, one of the things that I didn't tell you, or I didn't emphasize, is that the sphere is the geometry which will dominate in the sense that it has least action. So remember that this partition function, or the Hartle-Hawking path integral, is the sum of the classical action with the power of the coupling constant k, which was like 1 over h bar. So in the semi-classical limit, where h bar is very small, or Newton's constant is very large, then this will be dominated by the familiar result where we have a free sphere. So in the limit where we ignore quantum effects, we recover the usual statement that a cosmological horizon will emit an isotropic bath of radiation at finite temperature. But now we know how to include quantum effects. We know that if you include quantum gravitational effects, then there will be small corrections, in fact, exponentially suppressed corrections to this leading effect, which will give you deviations from the exact thermality that we're used to seeing when we study inflation. So those of us who have been doing computations of cosmological perturbation theory during inflation have not been wrong, because we've all been implicitly assuming that the Hubble radius is below the Planck scale. But if we wanted to be very careful, we should have included corrections that are suppressed by e to the h over m Planck squared, which would have accounted for these quantum gravitational effects. And once these effects are included, the Hawking radiation will not be precisely thermal. It will not be a pure black body, and will contain in it some correlations, which are reflections of these quantum gravitational effects. Are there any questions on that? Okay. So, every talk has to have at least a couple slides that nobody understands. So I thought I might get those slides out of the way. Nobody includes okay, so I told you now how to find all of the classical saddles that will contribute in the classical tree-level approximation to the path integral, and the answer is that you go to Wikipedia. Now, I'd like to mention briefly how it is we compute the infinite series of quantum corrections around each saddle. So, one of the things that I failed to mention, but I should have, is that unlike four-dimensional general relativity, which has two local degrees of freedom, namely the two polarizations of a gravitational wave, three-dimensional gravity has no local degrees of freedom. So in 4 dimensions, a metric has 10 degrees of freedom. You remove 4 by the equations of motion, and 4 by the symmetries, and you're left with 2 degrees of freedom. In 3-dimensional general relativity, the metric has 6 degrees of freedom. You remove 3 by the equations of motion, 3 by the diffeomorphism or coordinate transformation symmetries, and you're left with 6 minus 3 equals 0 degrees of freedom. So if there are no degrees of freedom in the theory, then you might think that there are no quantum corrections. But you wouldn't be exactly right if you used that logic. The reason being that even though there are no local degrees of freedom, there are still a finite number of global degrees of freedom, which, if you want, you can think of as associated with the topology of space. And one still needs to compute the quantum corrections, including the effect of these global degrees of freedom. Now, in order to do this, there are really 2 ways to perform the calculation. One way is to work very, very, very hard and the other way, and in particular to compute an infinite number of Feynman diagrams, which could take all day. But instead, what I would like to do is to cheat. And the cheat that I will use is the fact that three-dimensional general relativity is secretly a gauge theory. And not only is it secretly a gauge theory, it's secretly a topological gauge theory. And so I can use the methods of topological quantum field theory to compute this infinite series of subleading corrections. Now, I don't want to go into the details of this computation because I don't think at this point they would be extremely illuminating. But I do think it's worth, however, emphasizing a little bit of the subtleties that appear in this computation. So, what we're doing here is we're using Chern-Simons theory, this gauge theory description, to compute an infinite series of subleading corrections to quantum general relativity. And this is a highly controversial and notoriously delicate subject. And the only reason that we were bold enough to do this is that we actually knew how to compute at the one loop level. We actually knew how to give a completely direct computation of the quantum correction. And the only reason we knew how to do the one loop computation for de Sitter space is that we knew how to do it in ADS space. And the only reason why we knew how to do it in ADS space was because of ADS CFT. So I think there's an interesting sort of bit of sociology here, which is that the chain of logic, the history of this is sort of interesting in that if it weren't for ADS CFT, we would have never been able to do this computation. It would have just been too damn hard. Okay, but I don't want to dwell too much on the details of the computation. Instead, I just want to end by giving you the answer and discussing a little bit the physical implication of this answer. So, the answer, it turns out, is that for Einstein gravity, the sum over geometries is infinity. Now, we encounter infinities all over the time, all the time in quantum field theory. But this is a rather different sort of infinity than the one that we usually encounter in quantum field theory. So often in quantum field theory, we're used to encountering infinities that can be removed, infinities that appear in perturbation theory that aren't physical infinities. This theory has those, but they're removed in the usual way through regularization procedures that one always does in quantum field theory. Instead, this is an infinity that appears in the sum over geometries. The problem is that we had an infinite number of geometries that contribute to the wave function of the universe. And unless something special happens when you sum something infinite, unless something special happens, you're going to get infinity. I don't want to go through the details too much of the computation, but it turns out that if one does the computation in general relativity, this is indeed what happens. However, it turns out that there are other theories of gravity, theories where one includes additional degrees of freedom, which resolve this problem. So one of the lessons that we have learned over the years from string theory is that general relativity on its own does not appear to be a quantum mechanically consistent theory. Additional degrees of freedom, namely degrees of freedom from string theory, seem to be necessary in order to get a quantum mechanically consistent theory. And now, when we're computing the path integral of general relativity, we seem to be finding precisely the same thing. So general relativity itself does not have a finite partition function, but a close cousin of three-dimensional general relativity, something which is known as topologically massive gravity. I don't want to go into it unless people are interested, but this is the theory that actually has a finite partition function. And so it is only in this theory that the Hartle-Hawking state appears to live in a Hilbert space where it has finite form. Okay.
So what is the, so this is your the calculation is 24 zeta 1?
Yes. Oh, zeta 1 is a fancy word for infinity.
No, but I mean it is the zeta function value 1.
I mean, this is,
so if I make it 1 plus epsilon.
I can't have string theory. I can't have no equations. I mean, why did I write infinity in this way? Usually in quantum field theory, our favorite way of regulating infinities is using zeta function regularization. So for example, everyone knows that 1 plus 1 plus 1 plus 1 and so on and so forth is minus 1/2, right? Yeah. And 1 plus 2 plus and so forth is minus 1/12, something like that. So these are the sorts of infinities that we know how to regulate in quantum field theory. But the one infinity, and this is the infinity that we call zeta of 0. This is the infinity this is the infinity we call zeta of -1. This is the infinity we call zeta of 0. But the infinity that's zeta of 1 is 1 plus 1/2 plus 1/3 and so on and so forth. That infinity is not your friend because that's the infinity that really is infinity when you regulate it in quantum field theory. So, yeah, that was, it's better, okay, I hate, okay.
No, it's good.
1 plus 2 plus 3 plus 4 is not really -1/12. We don't know that. As long as it's okay. Okay, so now, I've told you that this wave function appears to have finite norm, so let's now discuss its properties. Now this here, I'm actually, this is not in the paper that I referred to in the very beginning. So we had a set 2 papers that came out earlier. This is actually some unpublished work. What is the form of the wave function? Now it turns out that, so we are here calculating the wave function of the universe for universes with 2 spatial dimensions. So I told you that the Sitter space has a causal structure that looks like a square. So if you want to understand what the causal structure looks like, the easy place to study the wave function is in the far future. So let's study the metric up here, h, and let's study the wave function as a function of the metric when the spatial slices are very large. And I told you that you could vary not just the geometry, but also the topology of these spatial slices. So the easiest set of geometries to study are those when the spatial topology is that of a torus. So it's a donut. Now, a donut can have all sorts of different geometries. And what we would like to do is study the wave function as a function of the geometry of the spatial slice when the spatial slice is a donut. Now, how do I want to parameterize the geometry of a torus? Well, so what's an easy way to write down a torus? Well, an easy way of writing down a torus is to think of the complex plane, and then you can identify points in the complex plane. You can identify z with z plus 1, and also with z plus tau, where tau is some number which is some complex number. Then, as you vary the parameter tau, the geometry of this torus will vary. And it turns out that this wave function has 2 very interesting properties. So first of all, when the torus becomes very, very asymmetric. So for example, if tau is very, very large, so that the torus, sort of looks like this, then the wave function is very small. The wave function is peaked when tau has particular values that are of order 1. And in fact, the wave function is peaked when tau takes one of 2 values. These are the 2 peaks in the wave function of the universe. And what are those values? Those values are tau equals I. So what is tau equals I? That's when the torus is a perfect square. And when tau is equal to I, the torus has a symmetry, because it has a reflection symmetry. And likewise, the other peak is when tau takes this other value, where the torus now has a second symmetry, which is some sort of, well, I won't be able to draw it. It's a rotation by an angle of 120 degrees. So what we see here is that the wave function of the universe appears to vanish when the spatial slice is very asymmetric. And it has a peak when the spatial slice is symmetric. So now this is a very, very simple theory of gravity, and I am considering the wave function only in a particular regime near Spry plus, and only for a particularly simple geometry. But one might ask whether this is a general notion which will apply more generally in quantum gravity, and whether the wave function of the universe, regarded as a function of spatial slices, has peaks when those spatial slices are highly symmetric. So that, I think, is a very interesting question, and one that at this point we can only speculate on for more interesting theories of gravity. But it's something that appears to be true for the simple theory of gravity that we've been discussing today. So, I have a few more comments regarding what's known as the DS-CMT correspondence, which is an attempt to generalize the holographic duality to de Sitter space. Let me just skip that, since I see that I'm already 1 or 2 minutes over time, and just end with a bit of a speculation. So, to my mind, one of the most interesting and challenging issues in physics today is the small value of the cosmological constant, which is either 0 or a number that's of order 120 orders of magnitude below the Planck scale. So, generically speaking, in a quantum theory, any number which is not, any dimensionless number which is not set to 0 by symmetry reasons should be of order 1. And so explaining this apparently small value is a bit of a challenge. Now, the mathematical structure of the partition function that I computed for you today, I think gives at least a possible indication of how we might resolve this puzzle. So the partition function was a number, but it was a number that depended on the coupling constants of the theory. And in particular, it depended on the cosmological constant, and it depended on the cosmological constant through the dimensionless ratio k, which was the curvature radius in units of Newton's constant. And in order for the partition function to be finite, this number k had to satisfy a certain equation. And it was a certain number theoretic equation. Now, for Einstein gravity, it was an equation with no solutions. But for a slightly different theory of gravity, which is known as topologically massive gravity, it's a very simple equation. It's the statement that the curvature radius, or the cosmological constant, in Planck units has to be an integer. That's as simple. So for those of you who studied three-dimensional quantum gauge theories, this might not
By 3D gravity, we are still thinking of 2 plus 1.
Absolutely.
So, because I guess otherwise,
This would not
might
be.
have heard of topologically massive gravity, and that's the only thing we would be doing now.
Yeah. No, this is, there's a, yes. This is only in a world with 2 spatial dimensions, unfortunately. Now, so this is the quantization rule that you get when you study 2 plus 1 dimensional general relativity with this particular additional topological degree of freedom. And this is a rather simple quantization rule, which can be understood in any number of ways by thinking about 3D gravity. But the hope, and at this point it's really a speculative hope, is that for more realistic theories of quantum gravity, the equation which quantizes the cosmological constant might be more interesting and may even, perhaps, explain its small value. So that is a bit of rampant speculation, but I think no talk would be complete without one, and so I think I'd like to end there. Thank you.
Yeah, given that we're already over time, maybe one question urgent, and otherwise we also are upstairs so we can discuss a little bit more. Is there one urgent question maybe?
I have an urgent question, but I'm happy to do it.
Anybody else an urgent